Hi, I'm Urara. My research topic is sleep ratio estimation for the localization of planetary rovers using proprioceptive sensors. First, I'll talk about introduction. Planetary rovers localize themselves roughly with odometry and IMU. Odometry is the most fundamental way for localization. It gets encoders data and converts it into how long the rover traversed, but it doesn't consider sleep. Visual odometry improves the accuracy by analyzing the pictures and compensate the errors. However, there are some cases where cameras cannot work well, like dark places and featureless terrain. Terra Mechanics have also worked on the sleep estimation. This uses, however, the soil parameters, which is actually impossible for rovers to know. So there is demand for a new localization method. This research proposes a sleep ratio estimator that does not use soil parameters or cameras. I'll talk about the method. The rover model is presented here. V is the rover speed, and V omega is the wheel speed, which is directly converted from omega. The sleep ratio lambda is defined as this. The inputs are encoders data, torque input, and the model of running resistance. This time I model the running resistance, but it can also be obtained using IMU and running force observer. When sleep ratio lambda is estimated, the rover speed is calculated. The rover position is gained by the integral of the speed. Next, I'd like to talk about the simulation. Two kinds of step torque were given. This time, the rover is assumed to run straight. First, I gave a step torque input, which was almost equivalent to the actual one that was used in the rover's field test, where the rover actually did not sleep at all, nor in the simulator. The sleep ratio was 0.03, but it can be said that although the rover slept a little, the estimation showed better results than without estimation. Second, half the stall torque was given to make a big sleep. This time the rover slept a lot, 0.41, and the sleep estimator made a difference. Finally, I'll talk about the conclusion. I couldn't conduct experiments, but I like to consider the fidelity of the simulation. Iris is very light, runs at uneven terrains, and has grousers on the wheels. So it will be susceptible to modeling errors and unexpected forces from the ground. So more detailed modeling should be done. On the other hand, if the modeling is too complicated or needs soil parameters, it will be difficult to use. So the balance between detailed modeling and easiness to use is important. As future work, I like to consider disturbances in y-axis vertical to the direction in which the rover goes. Even if the rover runs straight, it gets disturbance forces from y direction. Using the sleep estimator, a fusion with IMU and visual odometry could also be designed. If the sleep estimator is proven to be effective with sufficient experiments, these kinds of merits are considered. First, the estimator does not need cameras or soil parameters, so it works as a good redundancy for visual odometry. Second, the estimator has very short sampling time and has much smaller amount of calculation compared to visual odometry, so it can make up the gap between keyframes. I'd like to continue enhancing this method further. We really appreciate the sponsors for making this wonderful opportunity. Thank you for listening.